Section 4.5, integration by substitution. By the way, here is a reminder of some notations that get used a lot in mathematics. All right, let's take an example. The integral of 3x squared cosine of x cubed dx. Now this looks like we've got product going on. We don't have a product rule for integration. Maybe we can rearrange this a little bit and think about it a little differently. So let's write this as cosine x cubed times, and let's move that 3x squared down here by the dx. Now, here's an interesting thing. Cosine is the derivative of sine. What is the relationship of 3x squared to this? Well, it's the derivative. So remember that the integrand has to be a complete derivative of the antiderivative function. So if I think about this, cosine x cubed chain rule times 3x squared, okay? The antiderivative of that is sine x cubed. Let's just do a little check on that. Derivative of sine is cosine of x cubed times the derivative of x cubed is 3x squared and differential form dx. So when our integrand is complicated, the guess and check method that you've tried up to this point really doesn't work easily. So we really need to go to our u-substitution that we learned when we started taking derivatives. So let u be our inside function of your f of x, and let du be that derivative of u with respect to x. This means you want to be able to express the integrand as f of u du, and let's remember u is a function of x, so you can integrate easily. So if we look at this, this would be the integral of little f of u du. All of it has to be there. If the derivative of u is there, then this anti-differentiates to cap f of u plus my constant c. Now let's look at the example again and work it in terms of u. And let us remember, u is the most complicated part of your inside function. So if we let our u be x cubed, then du is 3x squared dx. Look at that nice differential form. And then if we regroup our integrand, we can get it in terms of f of u du. Here is cosine x cubed, 3x squared dx. Let's do our substitution. This looks so much easier to anti-differentiate than that, doesn't it? That's the whole point of u-substitution, is lets you integrate things that look very complicated. And so the antiderivative of cosine of u times the derivative of u is sine u plus c. And then we can go back in and substitute what our u was. Again, we can check our work by finding the derivative of sine of x cubed. Remember chain rule. The derivative with respect to x of sine of x cubed is cosine of x cubed, that's the outside derivative, times the derivative of the inside function 3x squared. All right, let's try the next problem. We can see that the most complicated part needs to be this inside piece of 1 plus x squared. While we're here, let's go ahead and find du, writing it in differential form. And now we're going to do a substitution. This is the square root of u and 2x dx. I have everything that I need for du, so I can substitute 2x dx right there for du because I have everything. And we can rewrite our u to the 1/2 there, anti-differentiate, and then of course we want to go ahead and clean that up and substitute back in our original function. These problems were easy because our u du idea was already in the integrand. In other words, here was my du is 3x squared dx, it was there. Had to rearrange a little bit, but it was there. Here was my du is 2x dx, it was already there. So when it's not there, we've got to do just a little bit of algebraic manipulation. So let us look at this example here. All right, we've got to pick the most complicated part for the location of our u. So our u is going to be 4 minus x squared, what is underneath the radical. While we're there, let's go ahead and find du, which would be negative 2x dx. Okay, and you will notice we have the x dx part, we don't have the negative 2. How do we get that negative 2? So to get our correct integrand, we're going to multiply by negative 2, but we can't just arbitrarily do that. We also have to divide by it. So I'm going to multiply my integrand by -2 over -2. And actually, in one step, I'm going to keep the -2 inside, that has to stay inside, and move the -2 in the denominator outside, so my integral is really nicely set up. Now we're ready to go. This is du, and this is square root of u. And we know that square root of u is going to be u to the -1/2. And now, this is so easy to anti-differentiate, right? This looked hard. This is easy. You've done plenty of these. Add 1 to the exponent, divide by the new exponent. We're going to clean that up. Dividing by 1/2 is times 2. And I can see that we can cancel our 2's here, and we get -u to the 1/2 plus our constant c, and then we can substitute back in what our u was. Okay, now we're going to do an even more complicated problem. I'll bet you can find the u pretty quickly. Think in your head, which one is the u? So underneath the radical is our u. So if that is our u, then our du from here needs to be 6x plus 6. Well, we don't have that. We have x plus 1 dx. So we actually need to multiply this by 6. So our du is 6x plus 6 dx, and I can accomplish that by just multiplying by 6 inside, which of course means we're going to divide by 6 as well in order to keep my value equitable. Now we're going to go ahead and substitute our u. You can see this would be the cube root of u. Okay, this is all of it, du. We're going to write that as u to the -1/3. I really didn't need this extra step, did I? And we're going to add 1 to that, so that's going to give us -1/3 plus 1 is 2/3. Dividing by 2/3, by this time you ought to be pretty good at knowing that when we divide by 2/3, that's the same thing as multiplying by 3/2, plus our constant c, the c of frustration. And we're going to reduce as we go. So 3 goes into 6 2 times. 2 times 2 is 4. And now we're going to back substitute in, and there you go. So you see, the most difficult thing is correctly identifying your u and getting the integrand in the form of u du. Now, let's look at this one. This one looks even more awful. But if you look very closely, we've got an inside function inside of sine and cosine, but we also have a sine cubed and a cosine. Now, I wonder how those are related. Well, it looks like cosine is actually the derivative of sine. So we could think about this problem that way. But we could also start with what we know to be true. Our u would be 2x squared plus 1, and the derivative of that would be 4x dx. I only need 4x dx, but I have 16x dx. So I can just factor out a 4. So I can bring this 4 out inside. Now, I could bring this in front of the integral, but for the moment, I'm going to leave it inside the integral sign because maybe something interesting might happen. So here is my 4 sine cubed 2x squared plus 1 cosine 2x squared plus 1, moving that factor of 4x down by my dx so I can see it. Let's go ahead and substitute u in. Notice that I have 4 sine cubed u. Another way to think about that, as we've talked about, is 4 sine of u cubed. Oh, if this is a derivative, where did 4 times something to the third come from? Well, it came from that thing to the fourth, the antiderivative. But let's look. We have a chain rule thing going on here. So if this is going to be part of my main function for chain rule, the derivative of this would have to be cosine of u times du. I have it. So this anti-differentiates to sine u to the fourth, which of course is written as sine fourth u, and then we can back substitute in. There's our answer. Now there is a whole nother way to think about this problem. If you didn't see the u du pattern, let's make another substitution. Now since we've called this to be our u, let's let v equal the sine of u, and therefore dv would be cosine of u du. So our integral from this point becomes that. Now that, you know how to anti-differentiate. It is so easy. It becomes v to the fourth plus c. But what was v? V was sine of u. What was u? 2x squared plus 1. So our answer is still sine of 2x squared plus 1 to the fourth plus c. Notice that I'm working horizontally, which I tell you I do not like, but I'm doing it to conserve paper. Okay. I am not putting equal signs here. These are arrows. That means this yields this, this yields this, this yields this. It's not saying this equals, 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 equals. You've got to be super careful. That is a problem on the AP exam called linkage, and you lose points for it. And when you're on a free response and it's 9 points and you lose 1 or 2 points due to linkage, well, that's just an unforgivable mistake. All right, now we're going to solve a differential equation. So here is a differential equation. How is this different from what we did before? So solve means I have dy dx. Solve means I want it to say y equals. So the first thing we're going to do is put it in differential form. And now I look at this and I can see I have something under the square root. So that's going to be my u, 1 plus x cubed. Okay. And my du is 3x squared dx. Ooh, I almost have it. I have more than I need. Now I look at this and I see what I have. And one way to think about this is I can write this right here as 2 times 3x squared dx. And if I do that, I see that this right here is du. So I'm going to get 2 du on top. Okay, and this is going to be the square root of u, which we know is u to the negative 1/2. And what I can do with this is I can bring the 2 out in front, so I'm not puzzled by it. And then we're going to anti-differentiate u to the negative 1/2. You've done that so many times before. And now we're going to multiply the 2 by the 2. We get 4, and now we're going to back substitute what we have. Okay. Once again, you can differentiate this and see that you get that. Now, you'll notice I wrote something interesting over here, and that is because this is our du, and I can see that what I had was 6x squared dx, which I can get by multiplying this by 2, and if I multiply this by 2, I have to multiply this by 2. So doing my substitution for 6x squared dx gave me 2 du. So 2 ways to think about that. Now, sometimes we have a very complicated integrand, and there's no way to get your du by multiplying or dividing by a constant. So we have to come up with another way of doing clever algebra. Okay? Reminder, you cannot multiply or divide an integral by a variable, only by constants. We've talked about that in class. So I look at this. So this is our u, okay? So our du is 2 dx. Now, I do want to notice, do not write square root of u. We're going to have to get our 2 dx, which means multiply by 2 and divide by 2 to get the du, and we're still left with that x there. So we do not ever want to have x and u in the same integrand. Now, you will see other videos of people doing this. It is bad form. Bad form. So we're not going to do that in this class. All right. So we can't multiply by a variable. We can't just multiply or divide by the x. We can't do that. What can we do? Well, you will notice I need to do a substitution for that x. So I'm going to take my u and solve it for x. You can see from above that we have 1/2 du is our dx. So now I'm going to do a factor by factor substitution. So we have x to be all of this. That's going to go there. The square root of u. And dx is all of that. Now that looks terrible, but we're going to algebraically clean this up, and it's going to be super nice. Like you can see the 1/2 and the 1/2 is 1/4, and that can come out in front. And you can see that this is the square root of u, which is u to the 1/2, which could then be distributed across this. And you've done many problems like that. So now it's old stuff. So the trick was doing the algebra to manipulate my integrand. At this point, listen to the rest of the explanation before you write anything down. And I'll give you time at the end of this explanation to write it down. All right, so as we can see, 1/4 can come out in front, u to the 1/2 times u minus 1 du. We can distribute that u to the 1/2, makes this very nice and easy to anti-differentiate. That is your only calculus step. We had the step where we took the derivative to get our du and the anti-differentiation step. And now you go look in the back of the book and that is not the answer. So now we have lots of algebra to do. All right. First of all, we can see that we have u to the 3/2. We're going to pull that out. Both of the coefficients have a 2 on top, and the common denominator of the bottom is 15. So we are going to factor out 2/15 u to the 3/2. 2/5 divided by 2/15 leaves a 3. U to the 5/2 minus 3/2 is u, minus 2/3 divided by 2/15 is 2/3 times 15/2. The 2's cancel, and I get a 5, and all of that factor is gone. Now the other algebra I can do is I can bring this 2/15. 2 goes into 4 2 times, and that becomes 1/30. And I go look in the back of the book. And of course, that's not the answer because we do have to substitute back in for u. So now I'm going to substitute back in for u, and I see that, oh my goodness, we have all kinds of work we need to do here. So we're going to distribute the 3, combine similar terms, and once again, I have more algebra that we can do. We can factor a 2 out of here. And that 2 can come down here with the 1/30, and we get, bum-ba-dum, there's the answer. So pause and write down all this work before we continue the video. So when we have a definite integral, this creates a problem with those limits of integration. If you use u-substitution, you must change the limits of integration. So u is going to be a function of g of x. In other words, whatever your u is, you're going to take that lower limit and that upper limit and substitute it into your u, and it's going to change your limits of integration. So let's look at an example and see why this is necessary. Obviously, this is similar to one of the ones we did earlier. Okay, and so sine squared of x, cosine x, it looks like we might call our u sine of x because we can see sitting right there, the derivative of sine x is cosine x dx. So here's my du, and this would be u squared. So we are going to look at what this function looks like. Sine squared of x, cosine x. Obviously, we don't graph the dx, but this is what we have to look at. And we're going to compare that to u squared. Okay. So you'll notice sine squared of x times cosine of x. You have to do a multiplication sign between the two functions. Okay, and so let's look at what that graph looks like. My window, I'm going to go from -1 to pi because I like to see the y-axis. And then I am going to look at my scale. I'm going to let it be pi divided by 4. That's how we get that nice little number. And we know that all values for sine go from -1 to 1. Same thing for cosine. So I'm going to let my values go from -1.5 to 1.5 just so I see everything. And my scale on my y-axis is going to be 0.5. So let's look at the graph of this function. So we're going to do some math. Look at that. Press 7. My lower limit is 0. My upper limit is pi over 2, so pi divided by 2. And it's going to shade that region. It's thinking. And it's going to give me the integral. So we know that this is going to be 1/3. Now let's go and look at my other function. I'm going to turn this one on because if I use u substitution, this will become u squared. Now we can't use u because these are functions of x, so I have to convert that to an x. But let's turn this one on, and you'll notice that I have made it a thick line, so I can tell the difference between it and the other one. And let's graph that one. Here comes u squared. We know what that looks like. Well, you can see clearly there's a lot that's getting ready to be counted. Now let's look at how we find the integral when we have more than one graph. I'm going to once again go to math, go to 7. See that little 1 right there? That means that's the function in y1. I want to now do the integral for the function in y2, so I'm going to up arrow, and I get a 2 here, and it's blinking on that function. And again, let's look what happens when I go from 0 to pi over 2. Do you see it's actually covered a whole lot more area? And that is not what our integral needs to be if I'm going to use u-substitution. So what we have to do is we have to take these limits and we have to put them in our u function and get new limits. So g of 0 is sine of 0, which is 0. That's nice. That stays the same. G of pi over 2 is sine of pi over 2, which is 1. So my 0 needs to stay 0, but my pi over 2 needs to become a 1. So let's look at that. Find the integral. We want to be on function 2, so I'm going to up arrow there. My lower limit is 0, and we found that we needed to change the upper limit to 1. Okay, just type in 1, and now it's going to see, look at that. It gave that region, and there's the integral. So hopefully I've given you a visual of why it is so important when you use u-substitution to be sure to change the limits. So since we are going to change our limits, we are now ready to anti-differentiate, and we can substitute and see how easy that was. Now, it is possible to do this problem without using u-substitution. It's really, really easy. All we have to do is recognize that cosine of x dx is the derivative of the inside piece. So sine squared is going to anti-differentiate to sine cubed over 3 from 0 to pi over 2 and evaluate it. But isn't this so much easier? Okay, let's do another problem. Let's look at problem 9. We want to integrate on the interval from 0 to pi over 4, the tangent of x times secant squared of x dx. You've probably noticed that secant squared is the derivative of tangent, so you have sitting right in front of you, u and du. So you could do this pretty easily without changing to u substitution, but because we want to get very skilled at changing to u substitution, we're going to do that. So here we go. 0, the tangent of 0 is 0. That stays the same. The tangent of pi over 4 is 1. So we are going to change our limits at the step where you substitute your u. That's where it has to happen. Very important. And we're going to anti-differentiate. I like to bring the 1/2 out in front. Substitute 1, subtract, substitute 0, and there's your nice answer. Now, isn't that nice and easy? And we could have also done it without substitution. We also could have done this if we had thought about it like this. If our u was secant of x, our du would be secant of x tangent x dx. That still gives the same integrand. I wouldn't have done it that way, but you can. All right, let's look at number 10. This looks terrible. You can see that our u clearly needs to be what's under the radical. So our u is 2x cubed plus 9. From here, our du is going to be 6x squared dx. So I have exactly what I need. So all I need now is to convert my 0 to 2. So substituting 0 into this gives me 9. Substituting 2 into my u function gives me 2 times 2 cubed plus 9, which is 25. So now, at the step where you substitute your u is where you substitute those new limits. And we have from 9 to 25, I'm going to go ahead and make this u to the negative 1/2. You are a pro at anti-differentiating that. I'm going to go ahead and bring the 2 out in front because it's just so much easier to do the square root of 25 minus the square root of 9. And there's our beautiful answer. Now, wasn't that so much easier? Once you commit to changing the limits, then keep your u and evaluate everything in terms of u. Do not go back and substitute what your u was. If you do, then you also have to substitute the old limits of integration. So, you're just doubling up your work. Two things we have already learned about odd and even functions. We know that if we have an even function, it reflects across the y-axis. So from negative a to a, you could make your life a whole lot easier by doubling 0 to a. Why is that easier? Because you get to substitute a 0 in when you do your evaluation of the integral. If f is odd, from negative a to a, the area above is going to cancel out the area below, and you have an integral of 0. And remember, we've talked about the properties of odd and even functions. So let us look at this problem. This is the graph y equals 2x. If you sketch the graph of it, you can see this is an odd function. If you negate the x, you also negate the y. You can see that these areas should cancel each other out. And there you go, 0. If you actually wanted to do the work, you could. Now, if we look at this one, we can see this is a parabola with the vertex at the origin. So I'm going to recognize that instead of from -1 to 1, I can double from 0 to 1 because I know that is an even function. And so now I just have to anti-differentiate. 3x squared gives me x cubed, and evaluate 1, subtract 0, and I get 2. And the proof of it, of course, work it the old way, x cubed from -1 to 1. You just might make a negative sign error here. So it's very important for you to know your integration of even and odd functions. So your 4.5 TPs are 3, 7, 15, and 71. See you next time.